Hello students, today we're going to talk about the factor theorem, and this is going to require us to look back at the remainder theorem from the previous lesson. Remember, if a polynomial p of x is divided by x minus c, then the remainder is the function value p of c. Now I have a quick question here. What if we do this and we get p of c equals 0? What if we have a value c that we plug into the polynomial and we end up with 0 as a result? Well, if 0 is the result, that means that the remainder is 0 when the polynomial is divided by x minus c. And if we can divide a polynomial by x minus c and we get no remainder, that means that x minus c is a factor of the original polynomial. So we actually have a name for this. This is called the factor theorem. The factor theorem. And it says the following. C, a number, is a 0 of a polynomial p if and only if x minus c is a factor of the polynomial p of x. This can be very useful for us. If we can find a number that is a 0 of the polynomial, meaning when we plug it in, we end up with a function value of 0, that will give us a factor of the polynomial. Let me show you how this is helpful. We'll look at an example. Let's let p of x be the polynomial x cubed minus 7x plus 6. What we're going to do now is show that p of 1 equals 0 and use this to factor our polynomial p of x completely. Okay, so first we need to show that p of 1 equals 0. We could plug in 1 for each of these terms, and it wouldn't be that difficult, but if we were doing this for another value, maybe 2 or negative 4, that would be more complicated, and so we're going to end up using synthetic division because this is generally going to be the easier way to go about this in the long run. So the value of c is 1, and the coefficients are 1, 0, because we have 0x squared, negative 7, and 6. Let's use synthetic division to show that p of 1 is equal to 0. So we bring down the 1 here, then we multiply. 1 times 1 is 1. Then we add 0 plus 1 is 1. Then we multiply. 1 plus 1 is still 1. Then we add. Negative 7 plus 1 is negative 6. We multiply this by 1 to get negative 6, and we add to get 0. Because we end up with 0 in the end, that tells us that this function, evaluated at 1, equals 0. Now, the factor theorem tells us that since 1 is a 0 of this polynomial, that means x minus 1 is a factor. So we know x minus 1 is a factor. This is very helpful, because if you look at the original polynomial, this isn't something that we know how to factor. If this was an x squared, we might be able to use the unfoiling method. But because it's an x cubed, unfoiling's not going to work, the AC method won't work, grouping won't work, there's no GCF. So this method is going to be helpful when we have a polynomial that cannot easily be factored using the methods that we've learned. So we're going to use this to factor. We know that x minus 1 is a factor, and to figure out what is remaining when we factor out an x minus 1 from the polynomial, we can divide it by x minus 1, but we've already done that. That's what our synthetic division did. Remember that when we do that division, the quotient comes from the numbers that aren't the remainder. So this tells us that our polynomial is going to be x minus 1 times x squared plus x minus 6. The coefficients here came from the numbers that were left over there. Now that we've factored out an x minus 1, if we look at the rest of the leftovers, we can use unfoiling to factor out that trinomial. So we need two numbers that have a product of -6 and a sum of +1. Those are going to be +3 and -2. And so by using the factor theorem and synthetic division, we were able to factor a third-degree polynomial that we would not otherwise have been able to factor. This is one of the important uses of the factor theorem along with the remainder theorem. Now, at this point, we have enough information to start figuring out what the graph of this polynomial looks like. We can figure out what all of the zeros are, so that gives us the x-intercepts. We also can find the end behavior, because the polynomial is a third degree with a positive leading coefficient, so we know it's going to be going up to the right and down to the left, and it's going to have 1, -3, and 2 as the x-intercepts, and then we can figure out in between those whether the graph is going to be going up or down, etc. I'm not going to graph this one right now because we don't really have any more room here, and you have graphed polynomials before, but in the example problems, all of those will also involve sketching the graphs of the polynomials. So you will get practice there along with the use of the factor theorem and the remainder theorem.